Hello everyone. In this lecture, we will be proving the conservative nature of the electric field, which is a very important characteristic to be aware of when you are analyzing electrostatic fields. So what exactly is this conservative nature? So if you remember your paper on vector analysis, you will understand what is a conservative field. A field is said to be conservative if its line integral around any closed path is 0. So you take any arbitrary closed path and you take the line integral of that vector field. If that line integral turns out to be 0 over this closed path, then we say that the field is conservative in nature. So if A is a conservative field, then the line integral of A around any closed loop C is going to be 0. So over here C, what is the C? C is an arbitrary closed loop. Okay, so it really does not matter what is the shape of C. It could be a perfect circle, it could be a square, it could be any arbitrary shape. It doesn't matter as long as it's a closed loop, because being a closed loop, that's all it matters, okay, for this relation to hold good for a conservative field. So now the electrostatic field is always conservative. So if we say the electrostatic field is conservative, what do we mean by that? How do you qualify that statement? We qualify it in this way. So suppose I have a test charge and we take this test charge in a closed path, okay, in a closed path in a region where there is some electrostatic field E. Okay, so we have some region. In this region, let's say there is some electrostatic field E, and we take this test charge along a closed path. Then the line integral along this closed path of the electric field is going to be 0, which is basically this condition. So here, of course, A was any arbitrary conservative field. So here we have specifically talked about a field which is the electric field. So this relation is the line integral of the electric field about that arbitrary closed path is going to vanish. So let us now consider the charge which is Q, which is placed at some point O. Okay, so we have some charge Q which is placed at some point O, and there is some path. Okay, there is some arbitrary path, okay, near this charge. So what is going to happen is, due to the presence of this charge, there is going to be electric field which is going to be set up in the surrounding space, including all the points on this path, on this arbitrary path. There is going to be some electric field. So now what we're going to do is, we're going to take a test charge and we're going to move this test charge along this path, this blue line path that we have seen. We're going to move this test charge along this path. Okay, so now I mark a few positions here. So the position of this charge Q is O. Then we have two positions on this path itself. One position is A, another position I call it as B. Then I refer to the position of this charge, test charge, because the test charge is moving from point A all the way like this, and it moves to point B. So the position vector of this charge Q is changing. So I refer to the position vector of this charge Q as R. And then I also need the position vectors of this points A and point B. So the position vectors of point A and point B are RA and RB. So now this charge Q, it is going to move, it's moving along this path. So along this path, so because it's a curved path, we could always divide a curved path into many such line elements, some segments. So let us say this is a segment, okay, this is a line element. That line element is DL. So there is a unit vector here. The unit vector along the radial direction. That unit vector is R cap. So if I displace this R cap from here all the way till here, okay, let's say I displace this R cap, because it's after all a unit vector. I'm always allowed to displace vectors like this. I displace this here. Then I find that the angle between this DL, this line element DL, and R cap, the angle between them is theta. Then if we take the dot product, okay, if we take the dot product of DL and R cap, okay, if we take the dot product of DL and R cap, that is simply going to be equal to modulus of DL, which is simply DL, times modulus of R cap, which is 1, into cos of the angle between the two. So it will simply be equal to DL cos theta. And this DL cos theta is basically the projection of DL along this unit vector, right? The projection of DL along this unit vector. And as you can see from the diagram, this is basically the increase in the magnitude of this position vector R. The increase in the magnitude. So earlier the position vector is here, now the position vector increases. So it's basically the increase in the position vector. So that is your dr. So dl cos theta is basically your dr. So dl cos theta is dr. That means dr is nothing but your dl dot r. So this dot product dl dot r cap will be equal to dr. So we keep this idea in mind and then we proceed. Now to move the test charge, I want to move this test charge. So how do I move the test charge? As we see over here, how do I move the test charge from A to B? So obviously I'll need some kind of a external force to move the test charge, because if I don't have an external force, this charge Q is going to continue to move along this dotted line, because you see, as you can see here, there is no sign mentioned to these charges. So whenever there is no sign mentioned to a charge, so by convention we need to assume that they are positive charges. So no sign, so that means we assume that both of these charges are positive. So if I place this charge Q and I just leave it like this, it is the only force that it is going to experience is going to be the electric force. So, and that electric force, the electrostatic force, is going to be pointing in the outward direction, because both of them, we assume them to be positive, so they will repel each other. So this charge is going to move in this direction. So the force is going to be along a straight line. But the path that is taking here, it's not a straight line path, right? So the only way that we can make it move along this path is if we apply some mechanical force. So we have to apply some mechanical force on this charge Q. So the mechanical force that we apply on this charge Q, that mechanical force, it must keep this charge Q in a quasi-equilibrium. Quasi-equilibrium means almost in an equilibrium. It's not exactly equilibrium, it's almost in an equilibrium. And in a quasi-equilibrium against the electrostatic force. And what is this electrostatic force? The electrostatic force is simply Q times E. Okay, and if we are able to do that, then we will be able to move this charge, the test charge Q, from A to B almost without any acceleration. Okay. So to understand this, what should be the relationship between the mechanical force and the electric force, let's have a look at this. So we have this charge Q, and then we have a test charge here. Then there is going to be a force. The electrostatic force will be always radially outwards. This is Fe. So if I want this to be in quasi-equilibrium, that is, if I don't want it to have, if I want this charge to have almost zero acceleration, then the force, the mechanical force that I must apply, the total force on this charge must be almost zero. So that means the mechanical force that I should apply, we should be pointing towards this charge Q. Okay, so I should apply a mechanical force in this direction, and this mechanical force should be almost equal and opposite to this charge Fe. And this same mechanical force which I am applying, this same relationship should hold good for other points also. So if the charge, let's say, is at this point, then the electric force is this way, so but the mechanical force must be pointing always towards this charge. So if we are able to maintain this, then we will be able to move the charge from any point A to any point B along this path. Okay, so as a result, this Fm, the mechanical force, is equal to minus Fe, which is QE. So this is an important point which is going to help us derive an expression for the work done. So the charge Q is moved so that at each and every point there is no acceleration which is imparted to it. So the work done to move this charge Q, okay, so how much of work do I need to do if I want to move this charge from point A to B? So the work done, as we all know, so who's doing the work here? That is what we need to keep in mind. So what is the work done? Look at the way the sentence has been crafted. The work done to move the charge from A to B. So who is moving the charge? Not the electric force, because if it was only the electric force, it would just move it in a straight line. So who is moving the charge? I am the one. The external agency is moving the charge from A to B. So who is doing the work? The external force is doing the work, the mechanical force. Okay, the mechanical force is doing that work. So therefore, if I want to find out what is the work done to move the charge from A to B, I should be taking the line integral of the mechanical force, okay, not the electric force. And this mechanical force, as we have seen, is equal to minus QE. So I will replace this with minus QE, get minus Q outside, so it will be the line integral of the electric field from A to B. So what is this E? So we can see here what causes this electric field at all these different points. The source of this electric field is this charge Q, and we already know what is the electric field due to a charge. The electric field due to a charge is 1 by 4 pi epsilon naught Q by r square into r cap, where r cap is the unit vector. So we have this relationship which we have already seen in the previous slide, that is this dl, when I take the dot product with r cap, we will get dr. Okay, So we have these three equations. Work done in moving this charge from A to B is equal to minus Q integral of E from A to B. E is 1 by 4 pi epsilon naught Q by R square into R cap, and dl dot R cap is equal to dr. So all we need to do is just substitute this over here, substitute E from equation number 3 to equation number 2. So therefore in equation number 2, this is what we have. So minus Q integration A to B, this E I replace it with this. So there is a R cap dot dl. Okay, so R cap dot dl dot R cap doesn't matter because the dot product is commutative. Okay, so we have I take this Q by 4 pi epsilon naught, I take it outside, so minus Q capital Q by 4 pi epsilon naught, then integration dl dot R cap. Okay, and this dl dot R cap is nothing but dr. So we have integration dr by R square. So integration dr by R square is going to be minus 1 by R. So that minus and this minus outside will cancel out, and as a result we will have work done in moving the charge from A to B. When I substitute the limits from RA to RB, is going to be 1 by RB minus 1 by RA times Q capital Q by 4 pi epsilon naught. So equation number 5, what does it show? You can look at the equation number 5. You see the expression. Okay, these are all constants. These are all constants. It only depends on the distance of the initial and the final points. 1 by what is RB? RB is the distance from the charge small q till the point B, and RA is the distance from that same charge small q till the point A. So it only depends on the distance between the charge which is causing the field and the initial and the distance between the initial and final points. So that means it depends only on the initial and final points. It is independent of the actual path that you take. Okay, it is independent of this actual path, okay, that you're taking to move this charge. So it depends only on the initial and the final points. Okay, only on the radial distance to the endpoints A and B, and it does not depend on the path which is taken. Okay, so which means if I suppose this was the path, this was the original path, the path that I had taken to move from A to B. So now let's say I want to move from B to A. Okay, if I want to move from B to A, what will be the work done? All I need to do is I want to find out what WB to A. All that will happen is, because it only depends on the radial distances to the endpoints. Now when I move from B to A, I could move along the same path, or I could traverse the same path, retrace my steps, or I could move along a different path. It's totally up to me. But what matters is the work done will depend only on the radial distances between the initial and the final points. So in that case, WB to A will be 1 by QQ by 4 pi epsilon naught times 1 by RA minus 1 by RB. So this is the expression that we will get, 1 by RA minus 1 by RB. Okay, so work done to move the charge Q from A to B, we have seen. The work done to move the charge from point A to point B, it is equal to WAB QQ by 4 pi epsilon naught 1 by RB minus 1 by RA, and the work done to move it from B to A, okay, the work done to move it from B to A is going to be Q capital Q by 4 pi epsilon naught 1 by RA minus 1 by RB. Okay, so the total work which is done to move this over a closed path, so this is an arbitrary closed path. You're going from A to B along this path and from B to A along this path. So together, if I just remove these points A and B, it'll form a closed path. Okay, so the work done to move over this closed path, total work done over this closed path will be simply work done to move from A to B plus work done to move from B to A. And when you add them, you see this is going to be the negative of this. So as a result, the total work done will be 0. Okay, and the work done is nothing but minus Q line integral, closed line integral of E. Okay, so minus Q E dot dl. So minus Q is anyway constant, so that will vanish. So we have a closed line integral of E dot dl is equal to 0. So this proves that the electric field is a conservative field. Okay, so this brings me to the end of this lecture on the conservative nature of the electric field. In the next lecture, we will discuss I'll introduce to you the idea of the electric potential, which is more helpful in actually solving physical problems. Thank you.